Welcome back, dear students, on the CEC Gurukul lecture. We are dealing with the IR spectroscopy. For characterization, we use the infrared radiation which strike on the matter, and then we can record the IR spectra. For this, we use the IR spectrometer, or we can say it is a IR infrared spectrophotometer. We are discussing the main parts of IR spectrophotometer. First part is the radiation source. Second part is the sample holder, which can contain the various samples like solid, liquid and gas. Next part is the monochromator and the detector. Finally is the recorder. So radiation source must be of the infrared range that can be absorbed by the sample. So it should be intense enough for detection and extend over the desired wavelength. Now what type of sources we can use? Yes, as we discussed, and the samples are solid, liquid and gas. Now monochromator, which is also the important part in the IR spectrophotometer. Various type of monochromator used for splitting of a light or to get the single wavelength of a light, which is are of the type prism, grating and the filters. Prism are made of potassium bromide, sodium chloride, and these are used to split the light. Second is a filter, which are made of lithium fluoride, and diffraction grating are made of alkali halides. These are used for the for the splitting of the IR radiation to fall upon a sample. Detector are used to measure the intensity of unabsorbed infrared radiations, and the detector like thermocouples, bolometers, thermistors, Goulet cell and pyroelectric detectors are used in this spectrophotometer. Recorder. The recorder are used to record the IR spectrum. That may be the printer or the display unit. These are the basic parts of the infrared spectrophotometer. Now you see in the diagram that there is a basic diagram which contains all the parts. IR source, second is the sample holder, sample compartment where we put the sample and the reference. It is in the form of the solid, liquid or gas, and then it pass from the mirrors arrangement and then fall upon a monochromator. After the monochromator, the rays fall upon a detector. The detector will give the IR spectrum. So this is the basic arrangement: IR source, sample compartment, then monochromator, then detector. What are the applications of infrared spectroscopy? Where we can use the IR spectroscopy? The main infrared spectroscopy we use in the research purposes. So it has been a great significance of the scientific researchers in many fields such as protein characterization, nanoscale semiconductor analysis and space exploration. Various gaseous, liquid and solid sample can be analyzed by using the IR spectroscopy. So in the research, IR spectroscopy plays a very important role. Identification of the compound quantitative analysis we can done by using the IR spectroscopy. Functional group information present in the molecules, constitution of the molecule can be deduced from the IR spectrum. The various peaks in the IR spectrum will give the information regarding the functional group present in the molecule. We know about the interaction among the molecules, how the molecules can interact with each other, that we can record by using the IR spectroscopy. Comparison between the dispersion spectrometer and the FTIR. What is the difference between the dispersion spectrometer, which is where from where we are getting the IR spectrum, and FTIR where we are getting the Fourier transform infrared spectrum? So what are the difference between these two methods? In the dispersion spectrometer, we measure an IR spectrum. The spectrometer takes several minutes. Also, the detector receives only a few % of the energy of the original light source. But apart from this, in the FTIR, we are detecting or receiving the 50% of energy of the original light source. Here, see in the diagram, this is the dispersion spectrometer. Here we are using the light source, grating, slit. Then here the sample after the light passed from the slit. To separate the IR light, a grating is used. By here you see on the left hand side a grating is used, which is used to separate a IR radiation, and then light source that IR radiation fall upon a slit. To select the specified IR light, a slit is used. So a particular wavelength of light pass from this slit, fall upon a sample, then detector will detect and analyze the sample. So this is the basic arrangement of dispersion spectrometer. And what is IR spectrometer? In the IR spectrometer, the spectrum which we are getting will be generated in a few seconds. Moreover, the detector receives up to 50% of the energy of the original light source, and it is much larger than the dispersion spectrophotometer. It means FTIR spectrometer is a efficient method to getting the IR spectrum. What is this FTIR? That we'll discuss. This now you see on the screen. Here we are having the FTIR spectrometer. You see on the screen at the bottom we are having IR light source, and there is a slit which is at a particular angle, and on the left side and on the upper side we are having a two mirrors. One is static and another is moving. An interferogram we will get that pass in the detector to get the IR spectrum. The interferogram is to calculate and transform the values in the form of spectrum by using the Fourier transform. So this FTIR spectrophotometer is different from the conventional IR spectrometer. Now we discuss further what is this Fourier transform infrared spectroscopy. Most of the modern IR absorption instruments use Fourier transform techniques, where we are using the interferograms, which is used the Fourier transform technique to get the output. So most of IR absorption instrument use Fourier transform techniques with a Michelson interferometer to generate the IR spectra or to characterize the molecules. So this Fourier was given by the Jean in 1768 to 1830. Then what is the Fourier transform? Fourier transform obtain an IR absorption spectrum. One mirror of the interferometer moves to generate interference in the radiation reaching to the detector. It means we are using the two mirrors. One mirror in this interferometer, in the Michelson interferometer we are using the two mirror. So one is the static and another is the moving. The one mirror which is moving will generate the interference in the radiation reaching to the detector. Since all the wavelengths are passing through the interferometer, the interferogram is a complex pattern. Then it uses the Fourier transform. used in both the qualitative and quantitative analysis. This how the FTIR works. On the screen we are having the FTIR arrangement, and this is attached with the display unit which gives the output. So how this FTIR works? FTIR requires the basic parts. One is the source, second is the interferometer, then interferogram, beam splitter, sample, detector, computer, moving mirror and fixed mirror. We will discuss one by one. First is the source. As we are dealing with the infrared, so the source must be of having the infrared energy emitted, and which is glowing on the black body source, and that ends at a detector. Second is the interferometer. The beam enters the interferometer where the spectral encoding takes place. Interferogram signal then exists the interferometer. Then beam splitter takes the incoming beam and divides it into the two optical beams. One pass in the one mirror and second is the second mirror. Then there must be a sample holder. Beam enters in the sample components compartment where it is transmitted through or reflected off the surface of the sample. Light pass from the sample which is in the sample holder. Detector, the beam finally passes to the detector for final measurement. Then computer, which gives the signal, output signal, where the Fourier transformation takes place. And moving mirror, as the interferometer contains the two mirror, one is moving and second is the fixed mirror. So on the both the side we are having the left side we are having a moving mirror and the upper mirror is the fixed. So two mirrors are important. Michelson, what is a Michelson interferometer? The Michelson interferometer works on the frequency domain and time domain, convert into the time domain, then coding the spectra, then decoding. That is given by the Michelson. And this Michelson interferometer is used to get the interference pattern. So this IR radiation spectrum based upon the interference pattern through the interferometer. So Fourier transformation infrared spectroscopy, where we are having the normal spectra of the frequency domain, where we are having the plot between the intensity versus frequency, but here the intensity as a function of frequency versus frequency, but here in the Fourier transform we are having the time domain also. CIT versus T, where T is equal to 1 by n is the frequency. This is called the Fourier transformation spectrum. It is a transmission versus the wave number. Each version of the spectrum contains the same information, and the peaks will detect that what type of material which we are using. Now the transfer interferogram to the absorption spectrum. Here see on the left hand side there is a interferogram which pass, and then we are getting the output as in the form of the absorption spectrum. Michelson interferometer based on the interference of the wave, which must be in the phase or out of the phase. If it is in the form of the in phase, then constructive interference we get, and if it is out of phase, destructive interference we will get. Here we see in the diagram that constructive and destructive, and then either we can get the highest intensity or we can get the zero intensity. See the various type of the wave signals. Next is what is a comparison between the dispersion and spectrometer and the FTIR that we have discussed earlier. So now Michelson interferometer, what are the various parts in the Michelson interferometer to get the interference pattern? One is the beam splitter, second is the stationary mirror, third is the moving mirror at constant velocity, third light source is the helium neon laser, it is in the infrared radiation range, sample interval, control mirror, velocity. So these are the parts of the Michelson interferometer. How FTIR spectroscopy works? It's based upon the optical modulator. So it is called the interferometer. The interferometer modules radiations emitted by an IR source produces the interferogram that has all infrared frequency encoding into it. So on the right hand side we are seeing the diagram. Here the interferogram, light fall upon a sample, then here we are getting the output. One mirror is fixed and another mirror is moving. Interferometer performs an optical Fourier transform on the IR radiation emitted by the IR source, so that we can get the output, good output. The whole infrared spectrum is measured at the high speed as compared to the conventional IR spectroscopy. What is the design of the Michelson interferometer? It uses the beam splitter for dividing the incoming IR beam into the two parts. We use the two plane mirrors for reflecting the two beam back to the beam splitter, where they interfere either constructive or destructive, having the high intensity or the lower intensity, which depend upon the position of the moving mirror. One mirror is fixed and second is moving, so this depend upon the position of the moving mirror. So here see in the diagram, one mirror is moving, on the upper side the mirror is moving and right hand side mirror is stationary, and the beam splitter is in between these two mirror. IR source, light fall from the IR source, light coming from the IR source fall upon a beam splitter. The light after splitting going towards the stationary mirror and the moving mirror, and after that it will coming back and we can record it. So position of moving the mirror as expressed as the optical path difference. This optical path difference travelled by the red beam minus the distance travelled by the yellow beam, as we see in the diagram. So the position of the moving mirror is expressed by the term optical difference, optical path difference, that is OPD. Now mirror movement are the mirror movement and the interference of a single wavelength beam we are getting. When the moving mirror is in the original position, the two paths are identical and the interference is constructive. When the moving mirror moves 1/4 of the wavelength, the path difference will be 1/2. The wavelength and the interference will be the destructive interference. Mirror movement and the interference of a single wavelength beam, where we have the mirror moves back and forth at a constant velocity. The intensity of the interference signal varies as a sine wave. Here the moving mirror will move with a constant velocity. So for the white line OPD, the path difference will be the 0. Optical path difference will be the 0. But the mirror is moving with a constant velocity. Now here you see in the diagram that how the mirror is moving with the constant velocity and how there we are getting the change in the spectrum. Now what is explanation behind this, or what are the steps in FTIR spectroscopy? Now if we see that we consider a single frequency component from an IR source reach the detector, where the source is monochromatic and the light is also coming from the source is monochromatic. So difference in the optical path difference, the two split beams are created by varying the relative position of the moving mirror to the fixed mirror. So the output will be generated by the two mirrors. One is the fixed and another is the moving. So difference of the optical path difference can be get by these two mirrors. Next is the two arms of the interferometers are of equal length. Two split beam travel through the exact same path length, so that we can get the constructive interference. The two beams are totally in the phase with each other. So we are getting the constructive interference and leads to a maximum in the detector responses. As we are having the maximum intensity, so detector can detect easily. This position of the moving mirror is called the point of zero path difference. At a particular point, all these two mirrors producing the waves in the same constant phase difference, with the constant phase difference. So the position of the moving mirror is called the point of zero path difference, that is ZPD. When the moving mirror travels in either the directions by the distance of 1/4, then the optical part changes with the 1/2. The two beams are 180 degree out of phase with each other and thus interfere destructively. So 1/4, as the moving mirror travels another 1/4 and the optical part difference is now 2 or 1. So we are getting the destructive interference. The two beams are again in the phase with each other and result in the another constructive interference. So constructive and destructive interference we will get when it depends upon the position of the mirror. When the mirror is moved at a constant velocity, the intensity of the radiation reaching the detector varies in the sinusoidal manner, as we see in the previous diagram, and it will produce the interferogram. And this interferogram is the record of the interference signal. This interferogram actually having a time domain spectrum and record the detector response changes versus time within the mirror scan. It depends upon the position of the mirror. If we are using the more than one frequency, then extension of the same process to the 3-component frequency result in the more complex interferogram, for which we have to summation of 3 individual modulated waves. So it will be very complicated. Then broadband source, IR source, in contrast of the simple symmetric interferogram, the interferogram produces with a broadband IR source display extensive interference pattern, and it is a complex summation of the superimposed sinusoidal waves, each wave corresponding to a single frequency. And absorption radiation by a sample, when this IR beam is directed through the sample, the amplitude of the set of the waves are reduced by the absorption, and the amount proportional to the amount of sample in the beam. The absorption must be equal to the amount of the sample in the beam if the frequency of set of the waves is the same as one of the characteristics of the frequency of the sample. So the amount of absorption of the radiation, if the good amount of absorption takes place, then the intensity will be the better. Then how Fourier transform infrared spectroscopy is created. The interferogram contains the information over the entire IR region to which the detector is responsive. So this information is the mathematical operation known as the Fourier transform converts the interferogram, a time domain spectrum displaying intensity versus time within the mirror scan, to get the final IR spectrum, which is the familiar frequency domain spectrum showing the intensity versus frequency. So output will be in the form of intensity versus frequencies. The detector signal is sampled all the small precise intervals during the mirror scan, and the sampling will be controlled, the sample rate of controlling by the internal independent references, a modulated monochromatic beam from a helium neon laser focused on a separate detector. So this is the Fourier transformation. We are having the time domain, then it converts into the frequency, which is the wave number. So intensity versus OPT, optical part difference, and convert it into the intensity versus wave number by using the Fourier transformation of PL. Thank you very much.